Right, see, every routing protocol except BGP, all other protocols do load balancing if metric is same for a destination via multiple paths. I repeat, if there is a metric, if there is equal metric to reach destination via various paths, up to 4 paths will be seen in the routing table, and all the routes that are there in the routing table will be used always to do load sharing, packet forwarding. So the route should come into the routing table. That's the important thing. If route is there in the topology table, not enough. Not enough. It should be seen in the routing table in order to use the route. So you no need to configure anything on RIP, EIGRP, OSPF, ISIS to get equal cost load balancing. You need not to do any configuration. If metric is same via various path to reach a destination, out of many equal cost path, any 4 will be dynamically picked and put into the routing table. In case if you don't like it, you can set the max path to 1, which means I don't want more than one path. Though we got many paths, only one is going to be used for packet forwarding, and which one, it's randomly picked. So this is about equal cost load balancing, meaning that the metric is same. What if we have different advertised distance like this? For E to reach Z, 3 paths C, B, and D. B, C, and D. Going where C is the best. The reason is the FD value is lower. The path with the path with lower FD is considered a successor route. So what is the successor value here? Can someone say what is the successor value for E to reach Z? What is the successor value for E router to reach Z?
20.
20. The metric via C is the successor because the lowest FD is what considered as successor value. Okay, next. How many backup paths will be seen in the topology table? So the primary path is via C. So let's not talk about that now. Let us talk about the backup path. How many backup paths will be seen in the topology table? Can anyone answer?
So 1
Why? Only
via
one.
B.
What happened to via D?
The advertised distance is
Exactly.
higher.
Feasibility condition says if a path need to be considered as backup, the advertised distance must be less than the successor value. Our successor value is 20 only, whereas the advertised distance via D is 25. So this route is not going to be even considered. Now, when we have a backup path, which is also called as feasible successor in the topology table. So let us consider this is topology table. You got Z destination with how many primary route? Only one successor, and that is router C. But there is also another route called the feasible successor in the same topology table, but not seen in the routing table. So what we do is we see this value. Now this is the successor value, and we need to decide what to multiply with the successor value so that the multiplied value, the answer after multiplication will be greater than this number. So when I multiply 20 by 2, I get 40. This is to tell EIGRP to consider all the routes whose metric is less than 40. So 30 is definitely less than 40. So route via B will be placed into the rerouting table. And as I said earlier, routes that are seen in the routing table will be used for packet forwarding. So the variance is a multiplier value. That's what you see in the previous page. What is variance? Allows the router to include the routes with metrics smaller than the multiplier value. Right? So you are telling the algorithm to consider the paths whose metric is less than 40. So the path which was there in the routing table, topology table via B now also appears in the routing table. Yes. The route is not only in the topology table, it is also appearing in the routing table. So don't think that if a route is promoted to routing table, it won't be there in the topology table. No. Topology table will always have the routes, feasible successor and the successor. Usually by default, successor will be there in the routing table. Now because we put variance, and feasible successor is available in the routing table. Now, so this number that you decide to use is based on the FD value of the alternate path. And there is no need for me to put variance 3, because variance 3 will give me 60. What is the use? We don't have this path at all in the topology table. So 2 is the best number to multiply. We cannot put 1.5. We don't accept decimal values. You don't accept. It should be a round number, integer. So we cannot say variance 1.5 or 1.75, something like that. So this is the best number for this example. Variance 2 is the best number. 3 will be too much. When you say 3, the answer is 60. So all the routes whose metric is less than 60. But where is less than 60? We don't have 45, we don't have 50 or 60. So try to keep as low as possible. At the same time, the multiplier value should be should be greater than the alternate paths, FT. Now, this is what we need to see in the lab. Our focus is to the destination 44444 from route 1. These links are same bandwidth links, though I have tuned it in such a way that they are unequal. How did I do that? If you go to router 3, show run interface serial 6/1. Not this place. Okay, 00. Not here. And somewhere I have changed the bandwidth or the delay. Show run serial 6/1. Yeah, you see. On router 2 serial 6/0, I have put metric bandwidth as 1000. Here it's 1000. Let's go to router 1 and check. Show run interface serial 6/0. You see, I have put 1000 kilobits, which is 1 meg. Whereas the default is 1.5 meg. So in all other links, it's 1.5. So here we did not change. Here 1.5 meg, 1.5 meg, 1.5 meg, but here it's only 1 meg. So path via router 3 is the best path. Show run section router EIGRP. I want to remove that variance and show IP route 4.4.4.4. And now you see the available path is via router 3. But the topology table, yeah. But in the topology table, we got path via router 3 as well as router 2. And the FD means successor value is the route whose metric is this. The metric, this one, is matching with the path going via router 3. That's the elected successor route. The route whose FD is this is what? Elected route. In here, the bandwidth is 1.5 meg, 1544. Whereas here, The configured bandwidth is 1000. As a result, when the bandwidth is low, the composite value will be high. Fine. Now what? As a result, there is only one successor. This is unequal. The metric is not same. This is unequal. So in the routing table, you will see the root whose FD is this. Even in the routing table, this is topology table. In the routing table, you'll see that same 2809. See, 2809. This is administrative distance. This is the FD value. You will not see AD value in the routing table. Whereas in the topology table, you see two paths. This is AD value and this is FD value. FD value slash AD value. And FD value, this is elected a successor. And this is what we call it as successor value. Fine. So good thing about this alternate path is it is satisfying the feasibility condition. What? The advertised distance is less than the successor value. Successor value is 28. Advertised distance is 22. As a result, this path via router 2 is a backup. It's a chosen one to be a backup. And you saw in the routing table there is only one route. But I do not want to keep the other route idle. Topology table says we got another route, but it is not in use, it's idle. I want to make use of it. Simple. Show IP protocol, you see. By default, maximum 4 paths can be used. So I'm going to make use of this. Sure. Right now the variance is 1. I'm going to change the multiplier value so that the other path which is there in the topology table can also be used for routing. Router EIGRP 100 variance 2. You don't need to say max path 2 and all. The reason is by default the maximum path it can support is 4. After saying this, show IP. Okay, the reason why I put 2 is if I multiply this by 2 times, it will be like 4,000 or 5,000 something. Starting with 4 or 5. So that will be definitely less than. So the answer multiplied after this, multiplying 2 is sufficient to consider this path. And you see there are 2 successors now. Earlier we saw only one successor. Earlier it was one successor. Now when I multiply this by 2, I get an answer which is bigger than this. So it is considered, this one is considered as another path for packet forwarding. Earlier I just showed you only one. It was just only one. Let me take you up. Higher, higher. Yeah. It was only one earlier. But now it says there are two successors because we have set variance. So as a result in the routing table, C2, even though the cost is not equal, you see 2. Is this clear?
Yes, sir.
Nice. Now, when you get time, you need to do this and see. Let's move on to the next topic. Okay, this is one not that important, but we should know. The reason why this is not important is in WAN, it is not, you don't use much EIGRP. If you'll use EIGRP, then consideration is this. You should know these things like we know EIGRP supports point-to-point network, also NVMe network. But EIGRP will use up to 50% of bandwidth by default. This is the saddest part. So in a LAN environment, if your 50% of your bandwidth is used, you don't care because you got too much of bandwidth. You don't care. But in the WAN, for every single bit we pay. If EIGRP is going to take 50% of your WAN bandwidth, your internet bandwidth, say for example via internet, you are trying to form neighbor with the remote office, which is not actually done in the real world because EIGRP is an IGP protocol. Here what we consider is assumption is okay, between India and Australia, you want to run EIGRP. What is there in the middle? Internet. So over the path that you might have constructed between India and Australia, 50% of bandwidth is going to be taken by EIGRP for EIGRP's exchange of information between these two routers. Right? So by default, 50%. If you have a tunnel and if the tunnel bandwidth is 100 meg, EIGRP will say I need 50% for me myself. So the balance 50 meg, the balance 50 meg will be for the data, traffic. So the management traffic EIGRP is going to take 50 meg out of 1000 meg. But this can be changed. That's what this topic is about. Next 3 slides, we'll see how to change it. Now, before that, bandwidth utilization over the WAN interface. Bandwidth utilization over point-to-point subinterface using frame relay. Here, they're just trying to give you an example why this need to be changed. Which one? This 50% EIGRP, 50% it goes and grabs it. but we should not allow it. Why? There's an example. When we have a point-to-point sub-interface using frame relay. See, when I say sub-interface, it's not physical. It is a physical interface, but sliced into virtual interfaces, sub-interface. If the physical interface is 100 meg, definitely sub-interface is not 100 meg because it's the portion, it's a part of physical interface. Sub-interface is a part of physical interface. So definitely it cannot be 100 meg. The sub-interface cannot be. But the problem is, even though it's a sub-interface, because it's a serial link, EIGRP will treat the bandwidth, consider the bandwidth as T1. What is T1? 1.5 meg. 1.5 meg is what called as T1. That's the bandwidth of serial link. That is the bandwidth of physical link. But EIGRP is going to treat the sub-interface as a physical interface. Because frame relay, where do you run frame relay? Don't worry if you don't know frame relay. It's not so important. I'll talk about that sometime. But what I want to say is, frame relay can be run only on serial link. And because you are using serial link, the bandwidth considered is 1.5. EIGRP will assume that you got 1.5. See, physical link, yeah, you may have 1.5, but the sub interface definitely won't have that 1.5. That is one point. Second point is, even though you got 1.5, the frame relay might have not given you 1.5. The frame relay connection may be whatever you have agreed, committed information rate. Whatever you have subscribed will be there. You will not be, you may not be having the complete bandwidth as a subscription. You might have not paid for 1.5 meg because frame relay is very costly. You might have paid for 500 kb, which is 0.5 meg. So what is your bandwidth in PVC? What is PVC? Frame relay tunnel is what called as permanent virtual circuit. Permanent virtual circuit. So you have purchased the permanent virtual circuit only for 0.5 meg. That's what you have paid for. That is what the ISP is going to give you. But this poor EIGRP do not know about this. So EIGRP, as soon as it finds the serial link, the WAN link, it thinks that you got 1.5 meg, in which 0.75 is going to be taken by EIGRP. But where is 0.75? We have not given that much of bandwidth. We have not been given, but ISP has not given us that much. ISP has just given us only 0.5 meg. That's what we bought, we purchased. But EIGRP says, hey, you got 1.5, give me 50%. And it goes and grabs this one. What will happen to that frame relay? Fails. Will there be any traffic passing through it? No. Because EIGRP itself has taken the complete bandwidth, this 1.5 and above it wants. But you got only 1.5, but EIGRP needs 1.75. So what need to be done in this is we need to go and tell EIGRP that we don't really have that 1.5. We've only got 0.5. When you say we've only got 0.5, then again it's going to take 50% of the 2.5, which is going to be 0.25. Problem solved. 0.25. So that is one point. Second point, this is in the point-to-point link. In the multi-point link, what is multi-point link? This is multi-point. Hub, and all these are in same subnet, but different location. Same subnet, but different location. Means point to multi-point, because all the points are in same subnet. If one of this is in point to point, and these are multi-points, then you need to do configuration separately for this and separately for this. We just saw point to point. Now we are seeing multi-point. If you have multi-points, you need to calculate how many neighbors you have and the bandwidth on the neighbors. That is what you need to consider as a bandwidth on the hub. See, EIGRP uses bandwidth of the physical interface divided by the number of neighbors on the interface to calculate the bandwidth attribute per neighbor. So what it is, you see this picture here. What is the bandwidth of hub router, which has got 10 spokes, and each spoke's bandwidth that is needed is 25 meg, because the committed information rate is 56. 56. 56 is the committed information rate. So we want to tell EIGRP that we have only bandwidth of 25, so that it can take 50% of that 25. We don't want to give EIGRP the actual. Actual is 56 kb. So instead of saying we got 56 kb, you are saying no, listen, we got only 25. So the EIGRP will take 12.5 out of it, 12.5 bandwidth. So we are telling EIGRP that we got only 25. And how many there? There are 10 spokes. So on the hub, it should be 10 times more than the spokes, because there are 10 spokes. It's multi-point. How many, when we say multiple points, how many here? 10. So 10 multiplied by 25 is 250. That's why you see here 256, and 256 is configured as a bandwidth. All right. So the configuration that you see is point to point, but I'm talking about the multi-point here, but the configuration that is shown there is point to point. Let's see multi-point here. Multi-point example. In this example, you have 3 spokes and you want to say bandwidth as 256. Actually, that is what CIR also, committed information rate. So you got 3 spokes. So you add the 3 and put it as a bandwidth on the hub router. And this one is point to point. C and H has got point to point relationship. and the bandwidth is only 56K. You say the 56K. Whereas EFG, they are multi-point. The bandwidth is same on all three. If the bandwidth is different, then you need to put them in different point-to-point links. Because the bandwidth is same and you want to keep them in a group, so we configure as point-to-point. And this bandwidth is different, so we put it in a point-to-point. The spokes which has got similar bandwidth, we put it as under the multi-point. Okay, anyway, this is what WAN consideration is. Okay, so three things we have seen here. One, EIGRP will consume 50% of the bandwidth. Number two, we may not be using the complete bandwidth because the committed information rate in examples like frame relay will be based on how much we subscribed. So we need to tell EIGRP what is the actual bandwidth, the subscribed bandwidth, so that from that it will take 50%. Now we can use both point-to-point and multi-point. If you're using point-to-point, you go under that sub-interface and say, like here, 56 bandwidth. If you got multi-point with similar CIR value, committed information value, then the sum of bandwidth on all this multi-point should be the bandwidth on the spokes router. Sorry, hub router. Router C is point-to-point multi-point serial interface should be configured with 768 because that is what sum of 256 plus 256 plus 256. All right, so any question on this?
No, sir.
All right. The summarization, manual summarization, global summarization. In the newer version, auto summarization is disabled by default. Manual summarization is done on the interface. We saw unequal cost load balancing by using the variance. We can make EIGRP to consider the path of the different metrics as long as it is there in the topology table that can be used. And then finally we saw if bandwidth is not exactly same as the bandwidth on the link, we can specify how much is given committed information rate. Frame relay is an old technology. That's why I say do not focus on that. No one uses frame relay. Maybe one or two in the world. Very rare, very old ISPs like Tata in India. Few portion of Tata network is having frame relay. It's a layer 2 tunneling concept with Del C number as the identification instead of MAC address. When we go to OSPF NBMA network types, we may see frame relay. Now it's not necessary. So let's move on to the next chapter. Authentication is very important for a routing protocol because when routing protocols distribute route, they should be given, or when an update comes, the receiving router should not accept it without proper verification. Because the route update is what going to determine the route in the routing table. So if an attacker wants to divert the packets via his own gateway, via his own network, it is possible just by giving routes to our router. An attacker needs to provide the route information to the router so that all our packets and stuff going straight to bank, it'll go via the attacker's network. As a user, you will not find it because when you access bank, you are able to access bank. But it's going through an attacker's network. You may have some plan. So learning route needs to be carefully done. You run EIGRP. What if the other guy also runs EIGRP? The same autonomous system number that you use. You use EIGRP 100. The attacker also uses EIGRP 100. Then it will. Then both will form neighbor if they are in same subnet, which is very dangerous. So before accepting someone as neighbor, you need to authenticate that someone. As I said, every protocol supports authentication. In this authentication, there are two types: clear text and MD5. EIGRP supports both. Sorry, EIGRP supports only MD5. Only MD5. Clear text is supported both in RIP as well as OSPF. OSPF and RIP supports both clear text and MD5. EIGRP supports only MD5. MD5 is sending hash of the password instead of password. So when we send along with the packet, we need to send the password. When we send the password, the receiver compares our sent password with his local password. When it matches, the receiver will accept our packet. Likewise, when the sender sends to us, we compare the authentication string on the packet with the authentication string configured on the local. If it matches, then we accept the packet. So when you enable authentication, what happens is EIGRP sends hello packet, update packet, every packet with authentication in it. But that password is not going to be a plain text. It is going to be hashed and ciphertext and hashed, encrypted and hashed. So only by using an algorithm, you will know what the password is. For authentication. So no one in the middle can understand the password because this password is sent in the form of hash values. That's what MD5 authentication. All right, so what is involved is a keychain, key ID, key string. Here it shows only this page explains what is simple password, what is MD5. MD5 is message digest, which has got the password, key ID. Using these two, a hash value is generated and sent between the operating systems. Right? So MD5 authentication needs key ID. if you see the command here, we go under the interface and say, I want to enable authentication on this interface, which runs EIGRP, let's say 100. And that authentication type is MD5. And then I need to call the keychain, which is already configured. So this is how we configure keychain. Keychain, and then any name. This name need not to match with the neighbor. Key ID should match. Key ID should match, and key string should match. There are two other steps which is optional. We'll talk about that. Let me repeat again. Say, for example, between these two routers, we want to enable authentication. You need to create a keychain first. You can have many keys inside a keychain. That's why you need a keychain. You may have many keys. Why do we need many keys? Because I want to have different password. From this time, 4 o'clock, January 2006, and forever, I'll be accepting this as the password, but sending only from this time to this time, after which I want to have another password. So if I will have different password for each month, then I need to have a keychain of 12 keys, so that even if one password is compromised, just for example, not possible, if it is compromised, it will be only used by the attacker for that month, because the next month the key is going to be changed. So we create a keychain with the keys, and we go to the interface and we call the keychain. IP authentication mode, EIGRP 100, MD5 is the mode. IP authentication keychain for EIGRP 100 is this one, R1J. Likewise, you do it on another router, R2. Alright, so between these two router, authentication is enabled. That is what explained here in the steps. First, create a keychain, key ID, key string, accept lifetime, send lifetime. This is optional. If you don't say this, it's going to be forever. From now, forever. And then we call the keychain under the interface. Before that, you enable the mode on the interface. Right, lab on this we will do in the next class. Now, the verification is neighbor should come up. If authentication is successful, neighbor should come up. Show IP IGRP neighbor, you should see neighbor is up. And when you check the routing table, the route should be there, shared between the routers. And you can also ping and verify the remote network should be pinging. All right. So this is also a command to troubleshoot, debug. Debug means dig deep the bugs. By default, it won't show you the conversation, that negotiation happens between two routers. In case if you want to see it, you can type this command debug EIGRP packet. Here we see that router 1 is receiving a packet, MD5 authentication, key ID is 1. Whereas router 2 is receiving a packet with key ID of 2. No, the key ID must match in order to form neighbor. Only the password matching is not enough. So you need to troubleshoot. Go and try to match the key ID or key string. See here they made a wrong password as the key. So it started saying invalid authentication. Alright, so we will do this authentication lab with troubleshooting later.